Rewriting a system of linear equations in row echelon form usually involves a chain of equivalent systems, each of which is obtained by using one of the three basic row operations listed in operations that produce equivalent systems. This process is called Gaussian elimination. It's after the German mathematician Karl Gauss. So again, our goal is that we want to use Gaussian elimination. I know that we know how to use, how to solve a system previously, like in Algebra 2, but again, our goal is to use Gaussian elimination, and so we are going to practice that. So use Gaussian elimination to solve a system. So we want to write it in row echelon form. So again, we want leading coefficients of 1. And we want it in a stair-step pattern. So we should have, for example, like the 1x, or, I won't do the 1, but like x plus whatever here, and then y plus here, and then the z equals here. Okay, so that's our goal with leading coefficients of 1 here. So here we have x minus 2y plus 3z equals 9, and then negative x plus 3y equals negative 4, and 2x minus 5y plus 5z equals 17. Normally, you'll see it written like this. And it's kind of helpful to do that so you know where your equations are. So we're going to keep equation 1 on top. It already has a leading coefficient of 1. And then we're going to eliminate, our first step is to eliminate the other x terms. Okay, now it just depends on what you have already, but in this case, I want to eliminate the other x terms in equations 2 and 3. Okay, equations 2 and 3. So in order to do that, I can go ahead and add equation 1 with equation 2. So I'm going to use these two here. So if I add it together, x minus 2y plus 3z equals 9, negative x plus 3y equals negative 4. So I get y plus 3z equals 5. So that's our new equation 2. So let's rewrite everything. X minus 2y plus 3z equals 9. And now we have y plus 3z equals 5. So this is a really nice example, right? We see that it's kind of doing a lot of the work for us. Then we need to write the last one. 2x minus 5y plus 5z equals 17. Now, in order to isolate our second one, we want to get rid of x in this equation as well, in the third equation, equation 3. So I'm going to multiply negative 2 to equation 1 and then add it to equation 3. So now I have negative 2x plus 4y minus 6z equals negative 18. I'm going to add that to equation 3. So now I get negative y minus z equals negative 1. So then I'm going to rewrite this. X minus 2y plus 3z equals 9. I have y plus 3z equals 5. I get negative y minus z equals negative 1. So you want to leave it as it is because as you notice, because I left it as it is instead of dividing by negative because I see I could, is that all I have to do now in order to get z by itself is just add equation 2 with equation 3. And so when I do that, I will get y plus 2z equals, not y, sorry, y cancels out. I get 2z equals 4. So I'm going to go ahead and write it as it is. So x minus 2y plus 3z equals 9, and then y plus 3z equals 5, and then we'll leave it as 2z equals 4. And then what we're going to do with that is we're going to multiply equation 3 by a half. So 1/2 times equation 3, and that'll simplify that further. So x minus 2y plus 3z equals 9. Y plus 3z equals 5. And now we get z equals 2. And so now we can use back substitution in order to solve for everything. So we have y plus 3 times 2. So this is our final equation. Y plus 3 times 2 equals 5. So y plus 6 equals 5, or y equals negative 1. If you notice, this was actually our first equation we did. Y equals negative 1, and then we plug it back in. We get x minus 2 times negative 1 plus 3 times 2 equals 9. So we get x plus 2 plus 6 equals 9, x plus 8 equals 9, or x equals 1. So then our ordered triplet is 1, -1, and 2. So again, our goal is to rewrite it in this form using Gaussian elimination. And so that is what you're going to try in this next example here. Okay, so solve this system of linear equations, again using Gaussian elimination, meaning that this shall be, at the end you should see that stair-step pattern for the 3 equations. So if you try this out, what you want to try to do is you want to eliminate the x's first. Equation 1 is fine because we have a leading coefficient of 1. And so what I did is I multiplied -2 to equation 1 and added it to equation 2. And I got -3y minus z equals -9. And so then that's my new equation 2. And then I rewrite it. So here's the system. Then in order to cancel the x's in the third equation, I multiply the first equation by -3. Add it to equation 3. I get -2y minus 4z equals -16. So then I rewrite my system, and here it is here. And now notice I didn't solve for y, so I just wanted you to see that I just wrote it here. So I have x plus y plus z equals 6, -3 minus z equals -9, -2y minus 4z equals -16. So I multiply equation 3 by -1/2, and so that's how I get the y isolated. And then what I want to do, because that's a leading coefficient of 1, I'm going to switch equation 3 with equation 2 because I want it in the second row. So then I moved it here. Now I need to solve for z. So I'm going to multiply equation 2 by 3 and then add it to equation 3. And I get 5z equals 15 for that third equation. So I wrote it here. Then I multiplied it by 1/5. And so then I find that z equals 3. So here is the system in row echelon form. Again, this is the goal. You must get it in row echelon form first with leading coefficients of 1. And then you back substitute in order to solve, and so you get 1, 2, 3.